Good morning to everybody, or good afternoon, depending where you are. Okay. So I assume that you hear me well in this case. Good. So first of all, I'm very happy to be here and to be the part of this conference. I really think that Julia community is something that is worth being inside. Okay, so just not to take too much time off, I will share my screen. Okay, I assume that you see my screen. Wait more. Yeah, you can hear me great. Oh, okay, I'm very happy to hear it. I, of course, just to remind you from the organizational perspective, there is also this pigeonhole where I also have this opened on the other screen. And if you would have any questions, you can both post them in the comment section of the YouTube video or in this pigeonhole. I would try to answer each question whenever it's possible. If some questions would be longer, I will just tell you to wait with it, but I will try to answer everything that I will be able to. Hello from Uruguay. First of all, what we want to achieve today and who I am. So I am a physician. During the last year of specialization in nuclear medicine, so basically it's like radiology. And I'm also the programmer and the senior data scientist in Polish National Science Institute. Today, I am not planning to show you the state of the art of the medical imaging or medical segmentation medical imaging, but I will try to show you what can be done and what can be done in Julia. Because what is, I suppose, quite logical, I consider Julia as the very good place to very good environment for medical image segmentation. Why and exactly how it looks like, I will get in a moment. So first, I assume that most of you do not have any knowledge from either medicine, either the or GPU programming. I assume some knowledge from Julia. If something would not be clear, please tell me. Basically, the whole strength of the workshops, as far as I understand this, is that you can interact with me, that you can ask me questions, and that I can clarify anything that is problematic on the fly. So do not hesitate. I suppose this is the most important difference between workshops and the video that we recorded, and you can see it later. So now, if you have any questions, please ask me. So first, I will introduce you to medical imaging data format. So how one needs to work with it, what are the challenges, some loading of the data and simple preprocessing using Monarium or simple ITK and Python call. Then I will show you how to visualize the data using my package MedEye 3D. Then we will show some way of dealing with multidimensional data using Julia language, using GPU with the Julia language, which is also very important, how the HDF5 dataset basically is working, and how the HDF5.gl how many volumes and labels to load? Oh, this is a good question. And this is what I want. Oh, wait a moment. Basically, it's enough to get one. One volume and one label is enough. Yes, from any source that you get. We will work on one example at the beginning. Yes. At the very end, I will show you also some neural network, how it is. Wait a moment. And in the end, I will show you how to get the neural network. In this case, of course, you would need more examples for it, but we will not do it live because it just takes hours, so it would be impossible. Is there any way to get a CUDA-ready Julia environment? Frankly, okay. Frankly, we will. Sorry. Frankly, it is very simple. Yes, you just load CUDA and you are ready. If you have the GPU card with the, if you have in the environment, basically in the computer that you are running, if you have the Nvidia GPU card, the CUDA.gl team had done perfect job, and basically it just works. Yes, so when you have this CUDA.gl package, you do not need any Docker. Yes, for example, this is one important thing when I'm using, for example, Python for data science. Yes, you can do it on the cloud. Yes, you can do it on the cloud. Julia Computing has such cloud, and yeah, Julia Computing is sharing it, but this may be any other cloud. Yes, it may be, for example, on the Google or anywhere else. Basically, yes, you can do any task. Yes, only the paths would be different, and this should be the CT scans. Yes, you should have CT scan and some label, and basically anything would be good. Okay, so it can be anyway. Which data test should we download from your drive if we want to follow you at home? Basically, task 9, if you want this. Discipline. Oh, I see that it's changed. About this dataset, I will get back in the moment. If you do not have Nvidia GPU card, you also can follow most of this. You would not be able to follow from the sometime, but I will tell you. At the beginning, the viewer should work without the GPU card, basically. No, at least without dedicated GPU card. Okay, so basically you can either have the CT.org dataset or the Splint dataset, so task 9 from the medical decathlon. Both would be good, and I will mention about them both. Yeah. So the link to the data is in the description of the YouTube video. Yes, so if you do not have yet the data, please start loading it because it will take some time. Okay, so if there will be any other questions, let me know. I will try to answer them on the fly. Okay, so about this, it's enough. First of all, what are the alternatives? Because there are far more established frameworks for the medical imaging segmentation. For example, the Monai, one that I'm using a lot, basically. It's implemented a lot of the state-of-the-art. And have a lot of tools, really. ITK, very old, very long history. It's over 20 years old, but it's also its strength. Yes? So it has a lot of algorithms. DLTK that I know the least. Inner Eye, that is quite automated, and so on. But if there are so many already very well established, very good frameworks for medical imaging, why I decided to spend the last year and a half on developing some tools in order to enable working in Julia. First of all, this is because of Julia itself, obviously. So Julia offers a couple of things that I'm extremely interested in and are extremely useful. So the most important, frankly, is interoperability. Interoperability is because of this property of Julia that it is not, it solves this two-language problem. Yes. So, for example, if you in Python, it's very hard to cooperate between different packages very frequently. Yes. If something is not built with the thought of the supporting the PyTorch, it's very likely that it would not work with PyTorch. Yes. In case of Julia, it's not the case. If something was built, it's very likely that it will work with pretty much anything. Yes, because pretty much anything is working with Julia arrays. Yes, more or less, at least. The other thing is GPU. Yes, about this I will get in the moment. Other thing is package manager. Basically, in case of the Python, I cannot work basically without the Docker. Yes, because the environments can be very complicated. In case of the Julia, this is really, really well done, and we do not need to. Oh, sorry, screen is not showing. Yes, very good that you are telling me. There was nothing here, but okay, now you see it. There was, yes, I was just talking. There was nothing interesting on the screen, just this one. But good that you are mentioning this. Thank you very much. And the other thing is that we have a lot of unexplored possibilities in Julia. So Julia has tons and tons of packages that are having implementations of a lot of mathematical modeling concepts that are very hard to achieve in Python. Yes. So just getting it all together. If you have something, if you want to perform some classical medical imaging, if you want to to perform medical imaging, yes, using some already established known algorithm, usually you would be better off in Python, yes, because it's already implemented there into big extent. However, in case of the Julia, if you want to do something new, if you think about some new algorithm, it's basically, at least in my opinion, far easier to achieve in case of Julia because it's easier to cooperate. Yes, to get some new idea from idea to execution and to use huge amount of tools that are already implemented. So this is the basic idea. Why Julia? And why I did it. Yes, so I did. I will get to this in a moment. So first of all, why this GPU programming is so important? When you have medical imaging, yes, this is some medical imaging data. Yes, so what you see here is the brain, obviously, but from computer perspective, this is a huge R. Yes, and meaning huge is really, really huge. So it can be billions of points, yes, because, for example, it can be 1024 by 1024 by, for example, 1000. Yes, so it can easily achieve billion points by for one image, and there may be multiple images per patient. Yes, in most cases it's not as big as I described, but it can be huge. When you have huge amount of data, we can get a lot from parallelization. So with such huge amount of points to analyze, we can divide the algorithm to work on each point or in each group of points separately. So the more thread we have, the more work we can parallelize. And in practice, there is really little limit in this. So this data is really good for parallelization for a lot of types of algorithms. That's why GPU, where we have a lot of threads, they have some limitations, of course, but GPU generally can have thousands of cores. Yes, CPU usually have 8, 16, 32. Yes, in the very, very top end, let's say. GPU, in the normal GPUs, can have thousands of cores, and this is game changer in case of this type of data. Yes, so when you are working with such huge data arrays, this will change the speed of execution 100-fold, even more. Yes, sometimes I had seen some algorithms that were 1000 times faster thanks to GPU. Okay, so this is about GPU. Why HDF5? About this very shortly. This is just a way how to organize the data. This was created for the high-performance computing. You can think about this as it's just files. Yeah, so we have groups like folders and data sets that are just multidimensional arrays. Yeah, so when you think about typical database, yes, it's usually tables. In this case, data sets can be multidimensional, which is critical for this case, because It has the support for the three-dimensional or four-dimensional arrays, and has metadata that is also very important, and to which I am getting now. First of all, as you heard, I suppose many times, in order to do anything in data science, you need to understand your data and what does this data represent. So, medical data has a lot of variability and a lot of formats that it can be set in. Yes, it can be in Dicom, it can be in Nifty, it can be in RAW, it can be in MHA, sometimes it can be in HDF5. So it's important to load all of it. Yes, it's important to parse all of it and preprocess all of it in the way that would be useful for you. Okay. Okay, so I suppose, to be honest, I do not understand what you are reading here. I do not know the Cyrillic or Russian. I don't know which one. Never mind. But if you have any questions, you can post. So now, when we are looking, for example, at this image, yes, this is the classical radiological image. What we can see here, we can see what are the physical properties of the bodies that are here. Yes, so whether this is balloon, yes, like here, filled with water, and empty one, we can see whether the RTG rays can get through or not. Yes, this is quite simple. Yes? So when you shine the RTG rays on it, you can just describe it, whether it can go through or not. And this is just the map that shows it. So when you look, for example, at this square, yes, when you see this rectangle, sorry, you can decide, you can say that in this place, a lot of X-rays get through, in this place, not much. So we have some map of physical properties of this glass. Yes, the same is with the body. Yes, so this is a map of some physical properties. Different study will mean different properties, but the idea is still the same. What is also important, you can quantify this property. Yes, so this radiolucency, or basically how easy it is to get for the X-ray to get through in case of the X-rays or CT scan. And different tissues, different substances will have different numbers associated. Because of it, we can easily imagine this as the multidimensional array. Yes, so each point will be usually, not always, usually some floating point number or integer that explains some value of this particular property in given spot. Okay, so in given spot we have given radiolucency. In given spot it is so easy to get through with the some types of radiation or not. Okay, this one is already know. Yes, in case of the CT scan, what is also important, we can view 3D images. Yes, we can do 3D images, but in truth, those 3D images are because we have a lot of 2D images. Yes, we'll get deeper into it in a moment, and we'll get deeper, particularly into CT scans. So I will concentrate on this for a moment. Yes, so in CT scans, basically what we do, we slice the patient. Yes, so we make this slice of the patient, then go millimeter or 2 millimeters, so depending on the case, in one side, get the other slice, get the other slice, get the other slice. Yes, you will see it in a moment. And then we process it, and then we will tell in which point how in which point how easy it is for the arrays to get through, basically. Yes, and here we have the image. Yes, so we can see that it is far harder to get through the bone, yes, than the eyes, for example. And this is what we can see. In the end, we have the array. Yes, and we know how to work with the array, basically. Yes, because if you are programming, I'm sure that you had been using a lot of arrays, and to some extent, this is always the same. But there are some differences. Yes, so apart from this, that each voxel, so voxel is this three-dimensional pixel, yes. Apart from this, that each voxel is representing some physical phenomenon, yes, the quantified physical phenomenon. The other thing is that it is also somewhere in physical space. What I mean by physical space, yes, I mean that when the patient is lying, yes, we have somewhere right, somewhere left, and it makes it's important whether it's right, left, superior, inferior, anterior, posterior, yes. So in which direction the patient is lying, where do we start it, yes. So where do we start counting, for example, millimeters from the foot, so from the head or from somewhere else. So where we exactly, yes. So I would like to know later, yes, for example, when I see the RI, whether the heart is, I don't know, 50 centimeters from the head or 40 centimeters from the head, yes. We need to be able to retrieve such data. Because of it, we need to store this metadata. So one of the metadata is like this, yes. So we need the origin, so where we started, and the directions. Without this, basically we cannot interpret it fully. The other thing that is even more crucial from the practical perspective is spacing. Spacing, we will see it in practice when we'll start the proper workshop. The spacing is the fact that the voxels does not have uniform dimensions. What do I mean? That when we have the array, we generally consider each element of the array as the same, yes? In case of the medical imaging, it's not the case. It's not always the case, at least. So the voxels has some dimensions in millimeters, yes? So it can be high and thin, or it can be more quadratic, yes? Okay, when the custom formats HDF5 Dicom are needed, why do not use ordinary file systems and folders? Basically, HDF5 is just something not so commonly done. It's something that I have implemented here and proven to be fast. Usually, data in clinical setting is used in Dicom. Yes, Dicom is some standardization of the data, data storage. And in nearly all hospitals, or maybe even all hospitals, the data is in Dicom. Yes, the other ways, so Nifty, HDF5, and others, usually are for scientific purposes. Why they are not just ordinary file systems? Because we need this metadata. I just mentioned the most important from practical perspective, metadata, yes? So what is the origin, what is the direction, what is spacing? But there are more, yes? For example, it is written what is the patient yes, gender, yes, what is the series that we have, what were the exact properties of the current that was used in order to generate the image, what is the device exactly, because it can matter. That can be thousands of things written in metadata, yes? So basically this array, yes, this three-dimensional array that we will work with will be always the same. And it could be written in some file, but this, in order to standardize this metadata, we need Dicom, for example. Okay, but very good question. Okay, I assume it's answered. If it's not, please let me know if you still want something more. Okay, so but just getting one more time to this. In case of the spacing, yes, we have this optical distortions. Yes, it's good to check whether there are some artifacts or not. Yes, and some information about the artifacts is also important from the perspective of the metadata. Yeah, very good. Okay, so this is the example. You would see it on my viewer, basically. How it does not look, yes? If you imagine the lungs that you have on your own, it's not so compact, yes? So it's wrong metadata, but I will not delve into it. You will see it later. Yes. And this is one more time, yes? You have some array coordinates, yes, like this point. And then you need to be able to say where physically it is, yes? So how many millimeters from other point? In order to know it, you need to know the direction, the origin, and the spacing, yes? So you need to know that, for example, moving 3 voxels left, right, means that you moved 3 millimeters, yes? Or 5 millimeters or 10 millimeters, yes? It depends on the spacing, okay? Okay, so now just 2 things to show that about the things that I implemented. So this is, for example, some mean execution time, yes, in case of the My Viewer and some classical viewers. So this is quite normal, both on Windows and Ubuntu. And this is the metrics in the logarithmic scale. Yes, so basically, this is not yet completely published, but you will also see it today. The metrics in Julia, when implemented by CUDA.jl, are order of magnitude faster than the best implemented CPU, and similar to the state-of-the-art GPU on the Monai. Okay, so we'll get into, you can see the code. Okay, so first of all, maybe I will increase the size. Can you see it well? Do you want it to get larger? Yes, is it good, or you want it to make it larger, smaller? Okay. Basically, I'm not on Discord. It's perfect for you. Okay. I'm not on Discord. Okay. Good. Okay. Thank you for feedback. I had not logged into the Discord now. I am just now on the Pigeonhole. So if you want, come here. You want larger. Okay, so I will make it larger. Okay. So I suppose it should be done well now. So first of all, we are in my repository. Wait a moment, I will just... Okay. So the link is also in the... here. The link is also in the description of the YouTube video. I will send it in a moment, just for everybody to be at the same spot. And in the source directory, we have this Julia notebook. Yes. The notebook test. Oh, never mind. And here we have the notebook that we'll work on. Yes, so I'm just sharing the link one more time for everybody to have it. Okay. Okay. And we are here. Okay, so I ask you if you had read earlier the description, I asked to download some data that basically any data with the CT scans and some labels would be good. And you also could load these libraries. Yes, so we are using a lot of libraries, so this could take some time. Yeah, so first of all, we just execute this and get the libraries loaded into our environment. I already have in this environment everything loaded, but of course, if you do not have it, I will. Okay, it's good, very good. So, and the second thing that we can already start is that we need to establish some paths. First, establish some path to the HDF5 dataset that will already create now. Yes, so just provide the path. So modify the path that I had added here, and just provide the path to some folder that exists. Okay, so the folder needs to exist, and then we can keep the name, so it will keep yes, consistent, but it does not matter. So I will give you a moment to load the libraries and establish some path. Yes. In the meantime, do you have any questions? In larger even. Okay. Okay. Okay, so I'll give you 2 minutes for this load library and okay, some new question. Have you also considered to calculate exposure time to ensure for cancer treatment with your program? Is it possible? Angle for cancer. Oh, you mean radiotherapy? Basically, there is nothing that would work against it. Yes, the most important thing about this framework, it's not closed. Yes, I just gave some visualization data, some helper functions to save the data and load it, but frankly, you can do it. Yes, because this is not like typical Python frameworks. Yes, this is created with the interoperability in mind, and it was very easy to establish basically in Julia. You can visualize my data, visualize your data using my visualizer. I will get into in the moment how to do it exactly. We'll spend some time with it. You can load the data in the arrays and do basically anything that you want. You can save them in the HDF5 format or not. If you want, you can save it in some other format. Do not use this part of the framework. Yes, you do not need to use the metrics at all. Yes, you can use only the visualizer. Yes, or you can use the metrics. Yes, to check, for example, the difference between the gold standard established by the radiotherapist and the output of the algorithm. Yes, so you can use any part of the program per se. Yes, so there is nothing that would prevent incorporating and developing some algorithms in the radiotherapy for using my tools, basically, and then other tools. Okay, and there are some more. Where is exactly located the notebook? One more time. The notebook is in this Jakub Mitura, yes, MedPipe 3D tutorial in the source, yes, and it's called Julia Notebook Test. Yes, I will get one more time the link to it, and I will share the link one more time on the in the comments to the YouTube. Okay, so okay, I will try to answer this. Okay, I edited my, but generally I answered your question in your question. Yes, so I did edited it. Okay, so is it possible to run this on online rep? Yes, yes. Basically, I use normal REPL of the Julia. To be honest, it's worked a bit better in REPL than in Python in the Jupyter notebook. When I'm working day to day, I always do not use Jupyter notebooks. This is just easier to show during the workshops what is happening and where exactly we are. But usually I do not use it. I just execute the parts of the code in the terminal. Each rep should be okay. Okay. So just to know, are there any problems at this point? Yes. Do you have any problems for a moment? Can I assist you? Okay, I assume that there are no problems. If there are, do not hesitate to tell me, so I will think how to solve them. So I assume that we already have the libraries loaded. I added this CUDA allow scanner true. This is some technicality. Basically, in order to have high performance code, it should be false. But in very specific points, I just needed it to reduce, to get the last reduction, let's say, maybe not, to get a single number from the array. It was very useful to get it at the very end. In my particular case, it was not leading to some problems with performance because it was just the final operation. Okay, here. So this is important point because in case you would work with it on your own, this may lead to a lot of headaches. When you are opening the HDF5 database, yes, this is the this is the vanilla, let's say, HDF5. This part, let's say, is not related to my framework at all. So when you open this, you need to supply the argument, whether it's write or read and write. Yes, when you would supply it like this, so it's write, you are creating new database. So you will overwrite the old one. So if you already had something there, it would be deleted. This is important. So if you do not want to delete what is already there, you get R+, for example, yes, or R+. But if you do not have yet anything, you just paste a W as write. Okay. I will destroy the old database intentionally because I just want to start from scratch with you. Then later we are getting some number of the patient. This is just a convention that I created. So we have the number from the dataset, basically. These are two hyperparameters that I will elaborate a bit more later. So how big is the area from which to collect data, and what should be the numbers of clusters. And this is also some technicality. I will tell you later a bit what is it. What is important also, as I mentioned at the very beginning, but I will tell it one more time. Yes, I'm not showing the state of the art. Yes, I'm not the idea, the purpose behind the code that I implemented here in this workshop is not to get the highest performance. It's to show exactly how it works. Yes, so I'm using very simple things and showing how to use my tools to some extent and other tools and how they play together. Yes, this is not to get the best results. So if you would not get very good results, this is quite probable that you would not get, because it will be variable between person to person, between data to data, between patient to patient. Yes, in this particular implementation, do not be afraid of it. Yes, you can have a very bad results, and maybe I would have also. Yes, because this is quite random to some extent, at least. With this particular implementation, I will show more stable implementation at the very end, but this is relatively slow to train. So there was some technical problems with the description to the YouTube video. I do not know who has what type of data is mostly represented, but there can be the spleen dataset, yes, from the medical decathlon, or CT-org dataset. Both of them would be okay. Yes. However, in case you have this spleen dataset, just to make it easier, yes, you get this data directory, so the folder with the spleen, and then you use those two lines in order to get train labels and train images directories. Yes, this part is just collecting the paths. Yes, so there is no magic here. We are just collecting the paths, the full paths of the files that we will work on in a moment. If you have CT-org dataset, you can pass it like that. Yes, you need to push all labels into labels folder, all volumes into volumes folder. Okay, so you need to do it manually. So you are getting the all labels, yes, so labels 1, labels 2, labels 3, and so on in the labels folder, all volumes, so volume 1, volume 2, volume 3, and so on in the volumes folder, yes, and get the path to the folder that contains the labels and volume folder, okay? Okay, is it clear for now? Do you follow? So here we are just collecting the paths to the data, yes? Basically, it's just important that you would have here. You can even, if you want, you can even just copy and paste it, yes? So if you get the train labels, yes, like this, and you will get here the, yes, the path, and just you have get the patient number 1, yes, and you have just a single path here, yes, it will be okay. So you just need to collect, get me here, yes, some path to the volume, yes, and to the, sorry, here is label, yes, here is image, yes. So you just need to get one path to the volume, one path to the label, yes, and it's enough. Okay, let's go on. Then you zip the paths, yes, so you create, basically the zipping looks like that you are getting from entries from one list, yes, and second list you have the A, B, C, yes. The first list, okay, it's Windows. You have the F in the second list, and it will create the list of tuples, yes, that will have the first element from the first array and first element from the second array, yes, the first element from the first array, second element from the second array, and so on. Spleen dataset URL is wrong. Okay. I will get it one more time. Wait a moment. The Gatlon. Okay, you can get here. I'm just showing it one more time. And here you can click the get data, and task 9 would be the spleen. Yes. Or you can download, but the CT.org is far bigger. Yeah. So CT.org dataset is bigger, so it's maybe hard to get it now. Yes, but never mind. Okay. So and then we are just choosing some pair. Yes. So this tuple is just single pair of the label path and image path. Yes. And you choose target spacing. Yes. So you will see in a moment how does it work exactly. But in case of the target spacing, we can change the spacing to something else. Yes. So we have some original spacing, and we can change this spacing. Okay. Oh, and I did not post the link to the CT.org dataset if you want. Okay, so CT.org dataset. Okay, so and here you have, if you want, I'm also posting the link to the CT.org dataset. If you have some problems with the Medica Degato, both are okay. Yes. In case of the CT.org, we have multiple labels, so we just need to modify the entries. Yes, so we will just keep the entry 1. Yes, because the entry 1 is deliver in this case. In case of the spleen, in case of the Medica Decathlon spleen dataset, we already have the spleen. So as you can see below, it's not needed. Yes. And we just pass the data to some other data format for convenience. What is important, and I'm working to change it, but for now, you should rather work with the 32-bit representation for my viewer. Yeah, so my viewer just understands, for now at least, it may change, the 32 bits. Yes, so it may be float 32, it may be the int 32, uint 32, but it needs to be 32 bit. It's related to how the data is passed to the OpenGL. Okay, there's some new question. What does changing the spacing mean in this context? Oh, okay, very good question. Yeah, we will see it in a moment, soon at least in the practice. I will have make some visualization. Okay, so I did not executed this, yeah, so it should execute relatively fast. So one more time, we are just loading the paths and using some path to load the data into the arrays. Yes, so the label R and image R, and you can see it's already loaded in my case. Now we manage the data using the HDF5. This is not required, but it's useful basically. So here, what I'm doing, I'm creating the group. Yes, the group, you can think about group as the folder in case of the HDF5. I create the group with the name of the patient group name. Yes, that we established earlier. Default value is 1. Yes, if you do not change anything. Then we save the mask before visualization into the dataset. And what is here? Yes, this is just a name. Yes, image and label set. So this is how it will be called, this dataset inside. And this is the type. Yes, so later when the data would be loaded from the data set, these types are important, yes, because this would be parsed in different colors, yes, and this could be parsed in different colors, yes. So the CT have different way to visualize, and the labels have different way of the visualizing. Yes, all of the labels are described in the met pipe, yes, because just for those that did not heard it, there are 3 tools that I implemented. You can use all of them or just one of them as you wish. And one is for visualization, MEDI 3D. Other is for metrics, yes, and others is MEDPipe connecting those and HDF5 data space. And we also write the attribute, group attribute spacing. Yes, you can add any other that you want. Yes, so this is not, the spacing is required, but if you need something else because your data has some special metadata, for example, you can add anything that you want, writing this group attribute and then retrieve it easily. Okay, so here we are getting to defining how visualization should look like. Yes, so in the MEDI 3D, MEDI 3D describes how each mask, how each array should be visualized. Yes, so in case of the, wait a moment, not here, sorry. In case of my viewer, all of the data is stacked on its own. Okay. I just will show something. Okay, for a moment, this one would suffice. So basically, when we have the data, yes, let's imagine this as the 2D data for a moment. Yes, they are in the layers, basically. So all of the data, so this one could be CT, this could be layer for the manual modification, this can be the layer for the label, yes. So they are over one over the other. Each is also described as the texture, just because how the OpenGL defines it. Yes, so the OpenGL is the library for the visualization. Basically, it's used, for example, for games. So it's have relatively high performance, and this data is in the layers. Each layer can have different properties how it is displayed. Yes, so for example, CT scans would be white and black and have a very specific clamping. We'll see more about this. Labels would have also other colors, yes, and will look differently, and so on. Yes, and PET, for example, would look also differently. Okay, so and here we can define some things about how we want to visualize it. Yes. So as you see here, I just get two texture specification. So the manual modification and algorithm visualization. Yes, but we already had loaded here the CT scan and labels. Yes, so we have 4 arrays total. What's important, when we just put the CT scans and bull labels, this will be saved and then loaded the texture specification automatically. You can override this by supplying your own texture specification. Yes, so you can put your own texture specification, get some colors. Yes, single color if you want just single color, and that will have varying intensity, or multiple colors. Then you supply color set. If you supply color set, basically the continuous mask should be true. Oh, that's not so critical. If you want the mask to be editable, yes, so to have the ability to modify it using the mouse, basically, you need to point the is editable to true. It's good to supply min and max value. It could be inferred, but if you provided the visualizer or will get proper bottom and upper threshold, yes, so intensity would look better basically, but it should still work without it. What's also important, I created utility function get some color. Yes, you can override this using some manually chosen colors. Get some color, just get some next color from the list. I had found somewhere in the internet the list of the contrasting colors, and this function just takes next color from the list. Yeah, so it's automated if you do not want to think about this. However, just one thing to know, when you are using this function, the colors may be different from execution to execution. Yes, so if it's important for you to have exactly the same colors each time you are using it, it's important to override it. I will show you in a moment how to override it. And this is the main function. Yes, so this is the function that takes patient group names. Yes, and wait a moment. Oh, I missed it. Sorry. Here, I did not execute this cell. Okay. Now it should be good. Yeah. Also, I left it intentionally. In order to increase performance, you can increase number of available threads. Yes, and this is the error that would be posted, the warning at least, and that would be printed if you did not enable the multi-threading in Julia. It can be done, for example, in the settings on the VS Code, but it will work still without it. Okay, so now if you executed this line, you should have something like this. Okay, so this is a viewer with the loaded CT scan, yes, and the labels. In case of the CT org, you would have the liver. In case of the spleen dataset, you would have the spleen. Okay, so now just to know, are there any problems? Does everybody got here? Yes. Maybe I will make a short break just to anybody to catch up, and then we'll go on and I will describe how to use the visualizer and the annotator. Okay. In the meantime, if you have any question, let me know. I will look into the chat and into the comments. Yes, and I will try to answer anything. But let's make some break, and we'll go on. Okay. Okay, so Okay, and I didn't told you, just to be sure. So let's get back at 1705. Okay, so at 1705, let's get back. Yes, so in 10 minutes, yes, in 9 minutes even. Okay, but of course, oh, I see some new question. Okay, what syntax error? You can show me what is syntax error, so maybe we'll get it. Yes, and everybody else has a break. But if you have this syntax error, tell me how it looks, and I will try to help you. Shader creation error. Oh, so this is related to some OpenGL problem. You are using this on the laptop or on the PC computer? And do you have some GPU? Do you have some GPU? Maybe this is the first question. Because layout syntax error is probably not Julia related and not related to this one. But in order to be sure, you can also try the different patient. Yes, so you loaded some paths. Yes, M1 Mac. Oh, okay. To be honest, I did not test this on the Mac computers because I do not have any access to this. What you are showing me here is the OpenGL problem. Okay. OpenGL. Okay, so I will not lie to you. I do not know anything about Macs, yes, and basically how macOS is working. But I see that the OpenGL can be installed in the macOS. Yes, so I would tell you, in case basically from the tech stack, yes, it's based on the OpenGL and GLFV. Yes, so this contains the definitions. In theory, OpenGL should work on all of the platforms. Yes, but as you mentioned, it does not need to be true, as far as I see. And as I googled it, it seems that OpenGL can be installed on the Mac OS. So I suppose it could you could try it. I hope it would help. Okay. One more thing that I had heard and seen also is that in case of the Linux, sometimes it gives the error. Say that there is the error that the application hangs, but you can ignore it. Yes, this just prints the error that doesn't mean anything, and it works. Okay, I hope it will help. Yes, so. And thank you for mentioning the problem. Okay. Okay, I will get one more time the. Okay, so I'm back. So I hope that there are no problems now. We'll delve into how to use the visualization. So first of all, yes, you scroll using your scroll in the mouse. Yes, so you get from up, down, up, down. This is medical data, yes. So we are 3D medical data, yes. As I told you, in case of the CT scan, those what we see now, yes, those so transverse scans, so those slices through the organism, are the has the highest resolution basically because they are the original ones, let's say. But we can also see patient from the side and from the front, yes. This is used by pressing space, and 1 would be sagittal, yes, so from the side. Space 2 would be from the front. Space 3 would be transverse. Now, what is also important, when you press F, yes, it's scrolling fast, as you see now. When you press S, it's scrolling slowly. Yes, so one more time. F for fast scrolling, and space 1, space 2, space 3. Yes, the commands execute when you release the keys. Yes, so you keep the space 1, 2, 3, and when you release, this should be visible. Okay. What's also important, as I explained to you a moment ago, the visualization is layered. Yes, so we have different layers on it. One layer is, as you can see, CT scan. The other layer is label. We also have 2 other layers, yes, for the output of the algorithm and for the annotations. With the annotations, this is relatively simple. You just click and drag, and you'll see the interaction, yes? So this, and you can see it's saved. It can be seen also on other images, yes, like here. So this is how the annotations works. Yes, you just click and drag. You can also increase the size of the annotator by clicking tab and plus, yes, or decrease by pressing tab and minus, even to very small. So tab and plus, tab and minus. All of this is described in the repository of the Medai3D. This is important because when we will later try to analyze the segmentation, yes, of the liver in case we have now, or in the spleen in other case, we'll use the data about voxes that are close to the annotations that we created. Okay, so but about this in a moment more. Yes. So these are the layers. We can show and hide the layers also. Yes, so we can, pressing Control and number, we are hiding the layers. Yes, so Control and number hides the layers. So now I hidden every layer. By pressing Shift and layer, you show the layer. Yes? So Shift 1 in this case would show the CT scan. Shift 2 will show also the liver. Shift 3 will show also the annotations. I've lost them. Yeah, here. And Shift 3 was the algorithm output, and Shift 4 is the layer of the annotation. Okay. What's important is that you press the Shift to see something and press the Control to stop seeing something. Okay. These are the most important. There are also others, but let's not delve too much detail for now. If we would have some time, I will give you more about how to describe it in more detail. If the visualization does not work to you, soon we'll get to more algorithmic approach that you would not need visualization for. And I will help you later in order to remedy this problem. Still, if you have any problems, please write it on. Okay, so I will just get this on the other screen for a moment. So we are here. Yes, we displayed already the data. We see what's the case. Yes, so we see that the gold standard label is like this. What we want to achieve? We want to achieve that our algorithm would have exactly the same properties. Yes, would have exactly the same position the output of our algorithm would give us the label that is exactly the same as the gold standard. Yes, so this is the gold standard created by some physician manually, and we want to repeat it by our algorithm. But before we do it, just a bit more playing with the display. Yes, so if you do not like the display that was done by the automatic colors, you can change this. So you can see here, for example, I changed the color of the manual modification and label set, getting manually RGB values. Yes. Yeah, so now I execute this. And we see the colors are different. What's important, also the labels the annotations were removed because I did not save them. Yes, but now I can recreate. Okay, no questions for a moment. Good. And now, another very important part that I want to show you about this spacing. We'll play a bit with the spacing. Does everybody follow? Yes. Anybody needs help? Yeah. Anybody needs help? Okay. If you want, let me know. But now, some of you ask, what about the spacing? Yes. So now we have the spacing 1, 1, 1. What does it mean? It means that we assume that each voxel has 1 unit of length, depth, and height. Yes. So it's isovolumetric, basically. Yes. So, and this is how we parse the data. Yes? So we change the data in order for it to be true. Okay, I see some question. Okay, NumPy not available. It's strange, but okay, wait a moment. There is either way. So you can try. Semi-automatic. Wait a moment, I will find just the snippet to share with you. Oh, here it is. Okay, in case it did not work, wait a moment, where is this? Okay, here. In case you have problems with the simple ITK loading, you can load it like this. Yes, so you can also load by Monai. So it looks basically the same. You supply the first and second. First argument is the path to the label. Second part is the path to the label. First to the image, second to the label. Sorry, and it will also return the tuple with where the first argument would be the array of the image. Yes, the second would be the array of the label. Okay, and I will just, I do not see the way to answer this question for a moment. So I will just modify your question. So you can use this function. It's load by Monai from image and label paths. Yes, because in order to install the NumPy, you would need to change it a bit. A moment, and I will just help you with it. It does not want to work with me. Okay. Right. Okay, well, can do it like this and fast. Okay. 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 So I will just save it. Okay. So now, as you get to the top, yes, you can load the MedPy 3D from the source. Yes, I uploaded the NumPy to the Conda environment. If you would rebuild it, it should work. Okay. So I hope it will help you. You can also try this Monai. Basically, I'm working to get rid of the Python dependencies, but this is work in progress. But if you have still some problems, you can just reload the dependency, yes, the data, and I hope it will go now well. Okay, where we are? We are with the spacing. Okay, so here, I hope that others does not have any problems. Okay, so we have this situation that we see the image like this. This looks normal, yes? If you imagine your hips, for example, have more or less such shape, yes, and so on. Now let's change it, yes? So for example, let's say that the third dimension, yes, so the height of the voxel is 3 units. So it's not 1 unit, it's 3 units. So now, what does it change? Yes. First of all, when you look at this, it looks exactly the same. But it looks the same because we did not change the X and Y direction. Yes, X and Y is the same. But here you see that the image looks compressed. Yes, it looks like the person would be pressed from top and bottom. This because the viewer thinks that each voxel from top to bottom has 3 units. Yes, and because of it, it needs to squeeze it. Yeah. If it would really be 3 units, it would look normally, but it's not. It's really 1 by 1 by 1, but we have broken it intentionally now to change it. Yes. Okay, and now let's change it to other value. Yes. Okay, and one more time. Yes. And now I change this to 0.5, yes, and we see that it's elongated, yes. We are not so high, we are not so thin, let's say. And you look at the hips, yes, for example, we do not have such a long hip relative to the rest of the body. Yes, so this is what the spacing means, basically. That if we get the spacing wrong, we get the distances wrong, and we get a lot of information lost. Okay. So, okay. So let's get back. Oh, before I forget, yes, let's get back to the original spacing. Is 1 by 1 by 1. This is how it looks like. Okay, and now, if you have CT-org dataset, so you see the lever, mark now using your mouse, yes, the somewhere in the lever. If you have the spleen dataset, mark it in the spleen. Okay. So now it's important not to forget to mark some annotations inside. It's also important not to have anything outside. Yes. If you have, just reload. It will be the simplest for now, for a moment. But we need some spots in the liver. Okay. So now, from those spots, what we would do, yes, On the basis, maybe what is the hypothesis? Yes, we have the hypothesis that the neighborhood of each of the voxels that we marked as the lever, yes, so each of these points that I pointed here, is representative for whole of the lever. Yes, so that each neighborhood of these points is similar to neighborhood of each voxel in the lever. So we are collecting the local information of the voxels around any given point, and we will use it for our algorithm to guess where is the lever in the whole image. Okay, so this is the hypothesis. This is the idea behind it. Very simple idea, very simple algorithm. Will give us some results that we can see and understand. So first of all, in order to get the information from around, yes, we need to know exactly where we are. The very nice thing about Julia is that it supports Cartesian indexing. Yes, so it supports these x, y, z coordinates. We can use it in a lot of different fantastic ways. One of the things is that we can just get Cartesian indexes of some area, yes, and just filter those that we are interested in. Yes, so we get Cartesian index of the area around the point, and we filter only those that are in the distance that we specified. Yes, this distance specified is the hyperparameter. Yes, so we defined it at the very beginning by a z parameter, as far as I remember. But it can be different. Yes, you can look farther away or closer. It depends on you. You can play with it if you prefer. But here we are just choosing the Cartesian indexes, yes, that are in the distance from the center voxel. Yes. Here we are filtering from the array that we annotated all of the indexes that has the values bigger than 0. Yeah, so all of the indexes that we annotated, basically, because we started from all zeros, so everything that is not 0 is our annotation. And here's basically the same as earlier, so we just get some patch around, yes, and patch around patch, yes, because we need to get all of the points properly. Here is important. So we get sample and mean and standard deviation. So around each of the voxel, we get this neighborhood. Yes. Maybe I will get the idea here now. Yes. So when we have this data, yes, this is a grid of voxels. We know that the lever is somewhere here. Yes. We chosen some voxel here. Then we know the Cartesian coordinates of it. We had defined some amount of Cartesian coordinates around, and in this green circle, yes, we have some set of voxels. From this set of voxels, yes, this is just array of numbers. We get the mean, yes, and the standard deviation. Oh, variance, and then square rooted it. But the important idea is that we get the patch that is the representation of the data that is here. Okay. Are there any questions? No. Okay. And this is what is happening in this get sample, mean, and standard deviation. As I said, this is just the example to get from the very basic some algorithm that works without any, let's say, magic, and without any deep learning for now, at least. So we already have some functions that can define it. So in order to do this, we need to get the access to the arrays that we have. Oh, I did not execute this. Okay, so we need to get the arrays. Yes. In order to get the array from the data that we defined, yes, we defined the data here, yes. So when we load it, we define the object main scroll data, yes, and this object contains all of the references to the arrays with the data. What's also important from the practical perspective, when we are looking at this, all of the data, so all of the arrays are living in the Julia. apart from this one that you see. Yes, so when we scroll, we each time scroll the new data. Yes, just the data about given slice, just one slice is living in the OpenGL context in the GPU. Yes, so it does not get a lot of GPU memory. It should work on basically any GPU, even integrated. And because the data is in the Julia, we can access this and modify this at the fly. This is one of the critical parts why I created this visualizer. Yes, because in most cases, when you have some tool to look at medical imaging, you need to send the data, whole data, frequently save this as a file and just load this as a file. Yes, you cannot modify it at the fly in most cases. There are some exceptions. There is Napari that was created and is also a very good tool, but in many cases it's very hard to achieve. And now it's also in Slicer notebooks, it's also possible. Anyway, here is very convenient, at least in my opinion. So we also, so now what we are doing, the most important things is happening here. So we get these coordinates and we create patch statistics from it. Yes, here. So we get all of the points, yes. So yes, here, we get every point. We get coordinates around, and we get some statistics about each point. Yes, and then we map it to get distributions. How we get distributions? We use the Julia package about the distributions package, and we just fit a normal distribution. Okay, now we are doing all on the CPU, so it can take some time, but it's quite intentional because it's very simple to see. Yes, and it's also useful to understand what is happening. Yes, so we are not doing so much work. Yes, we are just getting about each point around and its neighborhood. Yes, it seems like simple. However, as you patched any point, you did not patch one point. You patch, you get a lot of points. Yes, around. Yes, about 9 points around. So it's hundreds of points, and getting all of the neighborhoods, all of the standard deviations, all of the means, generally starts to be a bit problematic. Okay, it's not a huge problem yet, but it starts to be a problematic. That's why when we are executing this on the CPU, like now, it can take 2 minutes, something like this. We'll get to this in a moment. Yeah, now we have it. Yes, so it took 1 minute on my CPU. Without any parallelization, without any optimization, really relatively simple task, but we have a lot of data. Yes, that's why it is. It can be slow. Yes, and in this case, as I said, it's intentional. So, how to deal with this problem that it is not as fast as we would like to? There are two things. One thing is to use different hardware and different hardware techniques. The other thing is algorithmic. So let's start from the algorithmic perspective. Yes, so we have one more time just to have everybody on the same page. We have created around these points, on the basis of the data on these points, the Gaussian distributions. Yes, those Gaussian distributions gives us the probability whether the given argument is similar to the lever or not. Yes. So around each point, we create a different Gaussian probability distribution. But each Gaussian probability distributions is defined in order to show us what is the probability that this point belongs to the lever. Okay. So, but we have hundreds of them for now. We want to reduce it. How we can reduce it? This is just some idea that I have. It's also showing that you can use any package, any idea that you have, and play with it. I created some simple clustering. Yes, so at a moment here. Okay, so I created some simple clustering that basically from all of the probability distributions that are present, yes, compares them using KL Kullback-Leibler divergence and checks where are in this space, let's say, defined by the Kullback-Leibler distance, so it's basically some Banachs, never mind, where are each probability distributions, yes, whether they are similar or dissimilar. And the clustering just covers the similar distributions in the same clusters. Yes. So where they are similar, they are in the same clusters. And next, I'm choosing single probability distribution from each cluster to represent it. The idea is that if a lot of Gaussian distributions are similar, they hold the same data and they are redundant. Yes, so I get rid of this redundancy by first getting only those Gaussian distributions that are the most important for the task at hand. Okay, so they are the most different from each other. Okay. And then we are choosing those distributions. I've chosen 9 different distributions that are most dissimilar. Now, as we explained a moment ago, just getting the data of the neighborhood around each point that we have chosen was already a bit demanding task. But what we need to do now? What we need to do now is quite harder, basically. Okay. What we need to do now is we need to get voxel by voxel, yes, point by point, and there are millions of them, and execute the Gaussian distribution, yes, sample it, and certain sample. Generally, put the argument, so each voxel and some of its neighborhood, into each Gaussian distribution and take the maximum from all of these functions. Yes, so we get each voxel, neighborhood around each voxel, we get the standard and mean, standard deviation and mean. We put this data into each of the Gaussian distributions, yes, and we get the maximum from all of those executions. What is critically important, this is millions upon millions of operations. Relatively simple, but a lot of them. If you would do it without any parallelization, it could take something like half an hour easily, maybe even more. But we can do this parallelization, and how to achieve this. First of all, here I am defining some additional functions just to get the constants of the Gaussian distributions. Because here, as we see, this is the formula for the Gaussian multivariate Gaussian distribution, and you can see that a lot does not depend on x. Yes, so all of this that does not depend on x can be pre-computed. Yes, so like the normalization constant, like the inverse of the covariance matrix. Yes, it can be computed earlier. So we just need to calculate x, and we get x and calculate the probability from this formula. Okay. So how to speed it up? The best way, basically, I suppose at least, is to execute this in the GPU using this massively parallel framework that I described earlier. First of all, this is for convenience. This is how I like to do it. There are a lot of different ideas. This is macro for the iteration. What is macro? If you are not, if you get from some different language, the macro can be a bit foreign, let's say. But macro is just a way of the very smart, very advanced code generation tool. Yes, so when we would execute this macro, the expression would be executed here and would get access to all of the context here. What is happening here? It's relatively simple. So I will draw it in a moment also, but the important idea is that we need to know where we are and establish our position from this point. Yes. So in case of the In case of the CUDA, yes, we have thousands of threads, as we explained earlier. So we need to get the idea where we are. Yes, so where each thread is. So it needs to know in which point of the array it is present. So in order to do this, we use this thread ID X, block ID X, block dimension X, Y, and Z. Yes. When we know where we are, we can load the data from around in order to get these sparse statistics from each voxel, as I explained earlier. Now, when we already have this data from this area, we will iterate in the given area. Yes, so RR is this range in which we are iterating, and we also need to check whether we are not delving outside of the array itself. And this will iterate around each voxel. Yes. And now what is happening here? Here we are defining the kernel. Yes, the kernel, for those that does not have any experience with GPU programming, is the program that is executed in the GPU. Yes, this is using the CUDA.gl. Absolutely fantastic package. Basically, without the TimberSart, I wouldn't be able to perform any of it. Okay. And what is happening here? Yes, we are just getting mean. What is mean? We are summing up all of the values from this range. Yes, so we are doing iter around. Yes, so we are executing this multiple times in the given neighborhood, and then we are getting the variance, and by getting the square root of variance, we get the standard deviation. And then we save the output into the correct point of the array. One more time, in order to know where we are, we use the thread ID X, block ID X, block dim X, and so on. There are very good videos created in the Julia community for the TimberSart, and but not only, that are explaining exactly how it works, and they are extremely well done. What is also important, we need to define how many threads per block we need to execute. This is some technicality, but basically the threads in the GPU are organized in the blocks and warps, and all of these okay. And all of this needs to be managed basically during the runtime. So we need to decide how many threads and how many blocks we need to execute. In practice, in production, let's say, one should also use the occupancy API that gives us the best possible threads and blocks configuration, but today, for simplicity, I omitted it. Yes, and then we execute the kernel. What happens during this execution of the kernel? First of all, we need to have the data in correct spot. So if you are from the background of the dynamic languages, okay, did you face any uncallous access or race condition problems? Basically the race conditions are the thing that happens very frequently when programming in any parallel code. Yes, of course. In case of the uncallous access, yes. In this access is not much coalesced. Yes, this is not very well optimized from this perspective. Yes, because this is a very simple code. I do not want to get to too much details. Basically, what I had seen is very good is when you are getting two-dimensional kernels. Yes, this is three-dimensional, yes, but when you get is two-dimension, and when each thread block is getting one layer by one layer, yes, so it gets just down. Also, it's very nice if you can represent if the data is binary, for example, you can represent the data in the binary format. Yes, for example, encode the integers in the data in the bit representation of the integers. It's getting easier than to get memory coalescence. Yes, so and just for others that does not remember maybe about memory coalescence, this is a huge topic about memory coalescence and one of the most important to get the most of the GPU. Basically, for the GPU, one of the most important thing is when you load the data and how you load the data. Because those threads that has the GPU are not working on their own. Yes, they're working in groups. These groups are warps. Yes, warps of, in case of the Nvidia GPU, are the 32. In case of the AMD GPU, it's suppose 128, and they are called the front. But I don't know. I don't like. But in case of the Nvidia GPU, it's 32 warp. And they, in order to get fast data loading, they should get data that is close to each other in physical memory space. Yes, because when we have the three-dimensional data, it's still a list. Yes, it's a list that has defined where each dimension starts, when each layer, let's say, each column, each row starts, and when it ends by some metadata. But it's still a line of numbers, basically. Yes. So in order for the warps, in order for the GPU to work the best, we need to get the data from the spots that are nearby. Yes. So optimally, each warp, so each 32 threads, should have the data that is next to each other. So 32 consecutive places in the memory. Okay. This is very important from this optimization perspective. I did not delve into this here. I did not try it even in this spot in implementation of the metrics. So in this, let's say, more production code, it is implemented to maximize this coalescence whenever I'm able to. Of course, but I'm sure that it still can be done better than I did. I'm learning this, but still, there is a lot of a lot of other things that I don't know yet. Okay, I hope that answered your question. If there is still something more, let me know. Okay. So now we have this. Wait a moment, I did not execute this. So no, I did not execute this one also. I forgot to get a lot. Okay. Okay, then I will execute this. Then when I will execute this, and then I will execute this. Wait a moment. Apply Ghost kernel not defined. It is defined. Frankly, that's why I prefer basically the command, executing this in command line. It usually works better, but it will work also. So what is the important thing? Yes, we are doing here huge amount of work. Yes, orders of magnitude harder that we did when we were just finding the distributions. Yes, it then took us 1 minute. Yes, and here the huge work that we needed took only 19 seconds on my GPU at least. And it's not optimized code, yes, as you mentioned already. So it's not optimized code, and it's already very fast. Yes, if we would do it on the CPU, it would take, I suppose, half an hour if it would not be optimized. We still can optimize it and so on, but it would be very slow. Okay, so this is the idea, and now what we done, we executed. Yes, we executed the kernel, so we has established how much each voxel is similar to the liver or spleen, depending on which dataset you are using. And now we have yes, and we executed the kernel. What is important? in order to execute the kernel, we need to copy the data onto the GPU. Yeah, this is also a big topic in the GPU programming, that we do not, we cannot execute any algorithm on the GPU before getting the data onto the GPU. Yes, and the copying the data onto the GPU is happening like this. Yes, so you just wrap it the normal array in the Q array. This is one of the ideas, or you can get the copy too. This is other way. But in order to copy to, of course, you have already some Q array present already. Okay. Okay. Did one GPU allow you to store all the image data into global memory? Yes. In this particular case, yes. The data it is couple hundred megabytes for the image. I chose a not too big image, basically. And this algorithm is quite lightweight. Yes, so this algorithm does not pose big problems with this. If, for example, for training 3D neural networks, it will be problematic. Yes, we would need to create some mini batches. But this algorithm does not require a lot of free memory, so there should be no problems, particularly with the Splint dataset. Yes, the Splint dataset, I chosen this and I posted this because it has very small images that will not overrun your memory. But yeah, in some cases, of course, you need to patch the data into the smaller pieces. But this algorithm was chosen to get very low memory footprint, basically. Reduce operation where we are. Basically, in the metrics, I am using three-stage reduction. Okay. Oh, this is also important topic, so I will get to this. So, in case of the GPU, yes, when we are looking at the GPU, we have those thousands and thousands of threads. Yes. There are two things that are problematic that we usually do not think about when we are programming on the CPU. Yes. The first thing that is data moving. This is usually the very big deal. That's why this data coalescence that we had described earlier was mentioned. And the other thing that is very important is communication between threads. Yes. So imagine that you have 1,000 people and you need to communicate all of them at once. Yes, and to coordinate all of them. It's a hard task. That's why the reductions task on the GPU are relatively hard. Yes. So what is the reduction task? The reduction task is that we have information from all of the spots and we want to get some single or reduced output from it. Yes. So the simplest reduction is the sum. Yes. So when we sum, we get all of the elements and we just add them. We have mean, and there are thousands and thousands of possible reductions. Yes, limitless possibilities. In order to do this with the biggest, with the best performance, we do several step reduction. Yes. So first of all, we do reduction in the warp. Then you do reduction of all warps. Yes, in the thread block, and then you do reduction of the whole of the GPU. And if you have multiple tuple GPU between GPUs, so this is in case of the state of the art. Yes, in metrics it's done like that. Yes, so this metrics that I will show you later. It's the multi-stage process here. Yes, it could be done in the CUDA.reduce. Also, is very effective way to do it. And in this case, as you mentioned, it should be done like this in order to get more better performance. Yes, so I do not see where I did it, but I'm sure that I did it somewhere. Yes, so what Marushiro Banzuli, I'm sorry for mispronouncing this. Of course, this is a very valid comment. This is how it should be done. In this case of such a simple reduction, this would be a better idea in order to maximize the performance. Okay, thank you very much. Okay, so now let's go on. Yes, and here we already have this data. We need to copy this data one more time to the CPU because our visualizer, our tool for visualization, is getting the data from the CPU. We are dividing by the maximum element just for standardization to see it better, and refresh in order to get the data from the last layer here. And here we see this very nice, we can, okay. To be honest, I like this image. This is what we have yes, as a result. You should see something similar, yes? Whatever, basically, whatever you get the spleen or liver, it should look similar, because frankly, as you see, both spleen and liver has very similar properties, very similar local properties. So you get these points of high probability getting all around the spleen and liver. So spleen is here, liver is here. This is vertebral column, for example. If you have some questions about the anatomy, of course, you can also ask. So here is the liver one more time, and here are the spots of that our algorithm decides that there is a high probability that this is a liver. Yes, what's important, our algorithm also told that there's high probability that this is a liver also. Yes, that it's wrong, obviously. So what we can do next, yes, we see, yes, when we would, yes, get shift 2 is getting the mask back, yes. So when we get back the mask, we see that there are two kinds of problems. First problem is the spleen, and second problem is that we just got some points in the liver, but most of the liver is still not recognized as the liver. Yes, so a lot of voxels, yes, like here, like here, like here, 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 and so on, are not recognized as the liver by the algorithm, and this is a problem. But we know one thing, that if there is a point that has from each side high probability of the liver, it's probably a liver. Yes. So if you are here, for example, from all sides there is a high probability of liver. So probably this is all the liver. So we can use the data about the neighborhood, about the output of our algorithm, to perform the refinement of our algorithm. So our algorithm can get the idea that we have the liver also here and here and here and here, by looking that a lot of voxels around has the high probability. How to do it? The classical algorithm for this is the relaxation labeling. So just to get it one more time, this is to show you a lot of different tools, and this is, I suppose, the best tool available in the, maybe the best is to be, but I'm a huge fan of the parallel stencil, basically. So the parallel stencil is the library that enables you to get any stencil computation. As far as I know, this was created for the stencil computations for a modeling of the glaciers or things like that, but it works extremely well in this medical imaging domain. So what is the stencil operation? Just to for everybody to know, this is something that we already did. Yes, we have some point, and we get the all the operation is based on the data from around. Yes, so we get the data up, down, left, right, in some neighborhood, basically, of this point, and we execute the function on each point based on the information of the neighborhood. How it looks like this. Yes. So you have you define this parallel stencil. Parallel indices is the simplest one to work with. You define like this in order to be sure that our indices are not getting out of the array, and you choose the arrays. Yes, you choose the points that you are interested in. Okay, so I'm choosing here, yes, the -1 in x direction, yes, plus and +1 in x direction, yes, +1 in y direction, -1 in the y direction. So all points around, and I get some mean. Yes. So when I get this mean, this is the 7-point Newman stencil, basically. So I'm not looking in the oblique directions. And on the basis of this, I can define this relax labels function. So this relax label function will look around, will check what is the probability, the mean probability around, will check whether this probability around is above some threshold, yes, some rate, and if this is above this threshold, it will decide that this given point changes the label to the point to the thing that is typical for the neighborhood. So one more time, you are getting in single point, we are looking at the neighborhood. If there is a high probability that this is the liver or this is a spleen in the neighborhood, we are changing this point to being a liver. Yes. If there is a lot of, and the other way around is also working. Yes? So it's important. If you have a lot of noise, this will help to reduce the noise because noise generally will be isolated. So in case of the noise, it will decide that there is a liver, for example, somewhere in the, I don't know, brain. Yes. But there wouldn't be much voxels around that will also tell that this is a liver. Yes. So we are using one more time the data from the local neighborhood. And here we are defining the rate and the steps. Yeah? So how many times we want to execute this relaxation labeling and what is this rate? So basically from what threshold will decide that this information from the neighborhood is significant, more or less. And we can execute this. Yes. So when we execute this, 0.6 seconds. Yes, this is a magic of the parallel stencil. So this is already very well optimized library. And you see that our algorithm, yes, so our algorithm already knows enlarge the image parts, yes. So in case of the spleen also, yes, because there was a lot of voxels that decided that here. There are some points also in the stomach, yes, in the gastric mucosa, basically. But we are getting a better job. Still, there are a lot of points that are not marked as the liver that should. Yes, so what we can do? In this particular case, the situation is simple. We execute it one more time. Yes. And it's getting a bit better. Yes, you can see that now in these parts, nearly all of the liver is granted. Yes. However, we do not know, in order to get any algorithm to work, we need also to calculate how well we are going. And how well we are going, we need to have some number. So we need a metric. Yes. Basically, when you are looking for how the algorithm, how well it's performing, you have either the metric or the loss function. Yes, the loss function is usually defined when we want to minimize the loss function. Yes, so in the context of the optimization, the metric does not need to be easy to optimize. I define the metrics and I'm working on to getting some new loss functions. But for now, I have the metrics. And here we are not performing an optimization in this particular case, so this does not matter so much. However, in order to get a metric, we need to have data prepared. Yes, there are a lot of different metrics, but most of the metrics are based on the fact that that algorithms should be sure about the result. Yes, so we are checking each voxel, yes, one by one. And on the basis of each voxel, it should be either liver or not liver, yes, or it should be some label or other label. But now we have different situation. Now we have floating point numbers, yes. So our algorithm decides that basically in some places there is high probability, in some places we have low probability. Yes, so we need to binarize it. So this is also a very simple thing. We can do the kernel or parallel stencil, or we could even it would be better even to use normal array, CUDA arrays working to map it. But we need to threshold it. So when we have the value above some threshold, yes, in this case I arbitrarily given the 0.5, we would decide that this is truly a liver. If it's below, it's not. Yes. So we threshold the data. It should look like should look the same basically. because as we just thresholded it, so it does not change much from the viewing perspective. We can now also save the data, close it, maybe not for now. So in this is also important from the practical perspective. When you would already have some data that you want to save, yes, in this case, I decided to save a manual modification layer, but you can save any other mask output of the algorithm and so on to the HDF5 just to persist it, yes. Okay. So now we will think about what to do better. But let's first make a short break. If you have any questions, ask me. I am here. Yeah. So let's make a break till 18:08. Okay. So let's make the break till 18:08, and then let's get back to the ideas to show what we can do further on. I will look into the chat and into the pigeon, and if you have any questions, any problems, please let me know. Thank you, and see you in a moment. Ponoć tylko na Macach nie działa. No, nie wiem, czy bardzo dobrze, ale cóż. Tam dużo rzeczy nie działa. Tam działa tylko te rzeczy, które są stworzone na Maca. O, czekaj. Okay, so let's get back to this. So now, okay, so if you have any more questions, please ask me. I will try to address it. Make it open. Thank you very much. Yes, I've seen this just after time. Okay, so now let's go on with the what can be done better. Yes, so this is as you've seen, this algorithm was done from the very basics without any magic, let's say, and there's a lot of things that we can do better. But one of the simplest things that we can do better is just to tweak the parameters. Yes, I suppose that whether you started from the lever or from the spin, your image basically can be similar to it. Yes, in some cases there will be also a lot of artifacts in other places. Yes, so as I said, this is not something that was created to work extremely well. Yes, but we can get better. Yes, a bit at least. We can do the hyperparameter tuning. Yes, so the hyperparameter tuning is also very well established in Julia. So here I collected most of the things that we did earlier, just without copying it here. Because I got too fast. Sorry, we did not yet perform the metrics. Yes. Okay, so let's get back here because I forgot that I did not yet show you the performance metrics. This is also a very important idea. So here we are, what we are doing now, next thing, yes, next step. Here we already had threshold, so now we need to define the metrics and display the metrics. We can get a lot of different metrics. This is defined in the package documentation, what metrics exactly can be called. Here I decided to get two metrics in configuration struct. Yes, so Mahalanobis distance and dice score. Yes, so these two. Dice is very classical. There are a lot of works now that test that dice is not so good, but still it's the most widely used metric that is around, basically. And now what is important, you will see displayed on the image as dice and Mahalanobis distance at the top right, sorry, the values of it. What is important, the values will be different, yes, because these are different scores. In case of the spleen, basically your performance will be far worse. Why? Because when you are executing around the spleen, all of the lever would be the error. Yes, when you are executing from the lever, all of the spleen is the error, and spleen is far smaller. As I said, it can look very bad. It's do not be afraid of it. So in case of the spin dataset, but the spin dataset set is far smaller, so that's why it was also posted in the link, and this also works. So now just to get back to the idea about the metrics and how these different metrics what they measure. Okay, so what about what is so special about the medical imaging and that it needs some specialized metrics? Because it does it. So first of all, let's imagine the common problem that we have the lungs, yes, and in the lungs we are looking from the tumors. Yes. What is important from the numerical perspective is that the tumors are relatively small, or can be at least relatively small, relative to the whole volume. Okay. In case, and it is very frequently the case, that what we are looking for is very small. That's why when we are defining the metric that tells us how well our algorithm performed, we need to take it into consideration. So we need to take it into considerations that there is a huge misrepresentation. Yes. So when we are just so for example, if you would like just to increase the maximum squared errors, yes, or sorry, mean squared error, yes, MSE, or any other classical metrics, we would be the algorithm usually would converge just to very simple thing, that all voxels are background, because this would be very simple. If only let's say the 1%, for example, of the voxels are true tumors, and the algorithm would just tell that everything is the background. Yes, so there is no tumor at all. It will get 98 or something like 99, basically extremely good accuracy. Yes, very small error. Although it would be completely rubbish. Yes, it would be completely useless, but it still would get a very good metric. That's why we need to take into account this misrepresentation of different labels. And one of the ways how to get this into account is this dice metric. This is very classical, still very useful metric. However, when you think about dice metric, what it does, it basically takes into account how many voxels are really recognized, yes, in the structures, to how many is not recognized, yes. So let's say that this is our algorithm output, and this is the true case, yes. So the dice score will not look at all around, basically. It will mostly look at what is well recognized, yes, so that our output algorithm founded this part well, but it did not found this part, although it should, and this found this part, although it shouldn't. Yes, so we have this true positive part, yes, false negative, and false positive. So this is basically how the dice score looks like. And Jacquard and a lot of others get on the same idea. What is important, they do not take into account the distance. So when we are looking at the distance, so for example, from the perspective of the dice score, whether the mislabeled voxel is so distant or so close is the same. In order to take into account the distance, we need some distance metrics, yes, like this Mahalanobis distance. So when we are looking back on the image, yes, so Mahalanobis distance is not completely metric, so it's not normalized, at least not in this case, to the range between 0 and 1. But here you can basically get the idea that if you would do it a lot of time, yes, and compare between different cases, Mahalanobis distance will give additional penalty to all voxels that are distant from the true image. Yes, so the spleen would be heavily penalized because it's far away. And the voxels that are just next to, like here, for example, will be not penalized so much. Yes, they would be recognized as a small error, and this will be recognized as a big error. From the dice metric, this and this error, so this voxel here that is not in deliver and this voxel here that is on deliver, is equally invalid. Yes, and this is a big problem of the dice score. That's because a lot of researchers are thinking now about getting the metrics in order to look into it. Okay, so going on with this. Okay, so going on with this, we also have this hyperparameter tuning. Yes, and how to perform this hyperparameter tuning? In case of the Julia, it's really simple. Okay. And we just define some of the parameters, yes, and we define the amount of steps. So here we are defining the steps and the rate for our relaxation labeling algorithm, and we want to minimize the loss. Yes, in this case, we are using this dice loss just for simplicity. And here also shows why it's important for this algorithm to be relatively fast. Because in order to get any hyperparameter tuning, yes, we need to execute the whole algorithm multiple times. Here I'm just defining the 100 different points. They are not executed, not all of them are executed, because this is, at least I suppose so. But still, yes, it's multiple execution of the same algorithm. And in order to find the best configuration of the hyperparameters, yes. So one more time, this is just to show that we can use basically any Julia library to help ourselves. Okay, and it's done. Yes, so the best would be these 16 steps from this range that I chosen and rate 00008. It should not change so much, but we can execute it one more time with this. Okay, it needs to just to get through one more time through all of this. It's reduced the negative. Yes, all of the lever is covered now, and we have a lot of additional noise. Yes, and in this particular case, it minimizes the error. Yes, important. This is just because we have chosen dice score. With the metrics, it would be a bit better, yes, because those voxels will be heavily penalized. Just to show you what can be the problem. And here you can also the plot of the hyperparameter tuning. Okay, but okay, I just need to restart. And now, just for, let's say, a spoiler, I will show you on the spleen dataset. This is the perform the spleen dataset. What would be the output of the neural network? Yeah? So now we'll get to the different part, when I will just describe you how one can perform some simple training on the very simple neural network to get a segmentation output. I just need to. Okay. In a moment it will load. In the meantime, I will start to describe you the what needs to be done. Yes, so these are also files that you can find in the repository, just next to the Julia notebook. And here first is the load image. So what needs to be considered? Yes, first of all, of course, you need to load the images like. Okay. Load the images as you did at the very beginning. So load the paths as you did at the very beginning. Then we need to find the information which image is the biggest one. Why this is important, which image is the biggest? Because the neural network expects the same dimensions of the arrays that would be put into its. Yes. So when we would put, in order to put the array as the argument, yes, as the training sample, it needs to have exactly the same dimension as all of the other arrays that we put. So we need to get the idea what is the biggest one. But what is also important, we need to get this idea what is the biggest one after we change the padding. So we need to have the same padding in order for the neural network to get the idea well about the distances. Yes, so it needs to have the uniformized data, standardized data with the same padding. I had chosen here the target spacing of the 1/2, 1/2, 1.5, 1.5, and 1.5. So basically, there is some research that isovolumetric voxels, so voxels that has all of these 3 dimensions the same, works a bit better. Whether it should be 1, 1.5, or 2 is the open problem, basically. Oh, here. Okay. And here, so we just need to get the same spacing. When we change the spacing, the size of the array is changing also. Yes, because you can squeeze it or enlarge it depending on the case. So we change the spacing. Yes, getting to the spacing that will be uniform, this target spacing. Then we can change the size. It would be more performant to look on the size from the metadata of the image, but I will keep it from the simplicity and just to be very explicit what we are looking at. And then we are choosing the maximum x, y, and z dimensions. Yes, why we yes, maximum x, y, and z dimensions in order to pad the whole image to the required dimensions. We also want it to be divisible by some numbers, like for 64, for example, because of the unit architecture. I will show you in a moment in some image how it works. Okay, and then we are loading the data. So we are loading and padding the data. What is also important, when we are doing the interpolation, yeah, so interpolation is the process when we are changing the dimensions of the data, changing the size of the data. When we are doing the interpolation, we need to do the interpolation differently for the image and for the labels. Yes, that's why we have different definitions. Yes, so here we need to pass the true for the label at the last argument and the false to the label and to the first argument. In this particular case of the spleen, we need to also, when I was looking at the dataset before the workshop, I could also see that the tops and downs of the labels were artificially set to 1. Yes, so there was some error, at least in my PC. So I needed to set it to 0. And we save all of this into the HDF5. So after this process, we would have on the hard disk the prepared dataset. Yes, of course, this is extremely simplified preprocessing. Yes, in case of the MRI, we need also the standardization, bias rate correction, and there is tons of things that one could do, and in order to get the best performance should do. But we'll get to the most basic and most essential things here. Yes. Also, what is important here, I did not parallelize the code just for simplicity. We can parallelize it. Yes, there is a HDF5 parallel format of the HDF5, and of course, in this case, we would have the yes, n-fold, depending on the number, of course, acceleration. And yeah, this is just for checking. Here, okay. So here is the data that is prepared already. You see there is a lot of padding. Yes. For this case, I chosen the padding 0. It should be basically the padding the same as the corners. Yes. So in the state of the art, basically, one chooses the median of all of the 4 corners and set it as the background color. But here I wanted for you to see the padding. And here is the output of the algorithm. Yes, I will show you which one. Okay, so this is the output of the algorithm. This is a spleen, yes, and this works extremely well to see the spleen. So as you see, yes, it's extremely well describing where the spleen is, and this is very simple unit, very simple process. Although it has a lot of artifacts, as you can see. Yes, so I do not know exactly why this happens, but I have such artifacts, and this is some problem of the unit. Probably this is related to the fact that this is a 2-dimensional unit that is implemented in such a way in order to reduce the memory consumption. Okay, and now, but this is, let's say, a bit of spoiler, yes? So, and just one more thing, just to show you. This is the gold standard, yes? This is a gold standard, nearly the same in case of the liver, but of course without the noise around. In case of the spleen, sorry. So the spleen is nearly perfectly described by the unit. Okay, and what is important, this is also the image that was not seen by the algorithm. But however, let's jump into the unit implementation itself. So this is based on the unit implement. This is copied basically from the segmentations models.jl, the library, the open source library that have some implementations of different algorithms, different architectures. The unit that I found there was to my liking, but there are other units also implementations that are present. I will show you one later, just to describe how the unit hub works. Or maybe now I'll show you. Wait a moment. This is from the medical models, so the 3D unit, the unit that basically would work better, but has a lot of memory consumption. So I did not want it to use it here just to enable everybody to run it, even in weaker GPUs. But how does the unit works? Yes, basically this is, for those that does not know, this is how the Flux is performing is constructing the neural networks. So we have chain by the composition, chain creates basically the composition of the functions. Yes, so we have L1, then we have chain L1 and chain this one with L3 is the chain of the L3, L2 and something else and so on. We chain to the end. And convolutions is just the way how to look at the neighborhood. Yes, so as we are describing our very simplistic algorithm through most of the workshop, I have shown that using the information around from the area around can get us a long way. Yes, maybe not to the best algorithm, but still a long way. Here is the same. Yes, so basically why the convolutional neural network serves? Convolutional neural network serves because the convolutions are looking into the area around, and on the base of the area around, they compress this data into the reduced form, let's say, and in classic convolutions, it's basically like that. Yeah? So in classic convolutions, in classic segmentations, we have this. Maybe I will just write. Yes, in classic convolutions, we get some array. Yes. And we use the convolutions, yes, that we can exemplify as these squares. We have for some poolings, for example, max pooling, and we reduce the data just to 1 point from the neighborhood. Yes. For example, yes, there are a lot of possibilities, and we get the smaller neighborhood because we just pulled the information from the neighborhood. Yes, and then we can get it even smaller representation that summarizes all of the information. However, in case of the unit, then we have the deconvolutions. Yes, so we get one more time bigger and bigger. Yes, as you have seen the code, and that we'll get back into the moment. Why this is done? This is done in order to be able to get some skip connections between the layers. So we need to have this skip connections will work only if the layers have the same dimensions. So they need to, when we have done some pooling, then we needed to done some deconvolutions, basically. There is one very historic but very useful definition. What is the unit? Unit was defined in some old book as the shape and texture neural network. So why it's shape and texture? Shape because when we have these pooling layers, basically we get the idea, the compressed idea about the shapes of the things that we're interested in. But the information about the texture is mostly lost during these pooling operations. Still, in case of the medical imaging, the information about the texture, so about the neighborhood information, basically, is extremely important. So in order to preserve this information, we have these skip connections. Okay, this is the basic idea behind it. And you can see these skip connections here, residual connections between 16 and 14, for example. Yes, here are parallel. Okay. And one more thing. And this is also because of these poolings. This is also why I created this to be divisible by 64. Because in my case, I created the 4 layers, yes, 4 poolings. And in order for it to play well, it needs to be divisible by 2 by 2 by 2 by 2. Yes. So in case of the 64, and it was very useful, at least. It worked better. Okay, and now how we train it. Basically, we need to get the training case, validation case. Training case would be all of the case from 1 to 80 in the case of the spleen dataset. Then we have the unit. In case these 4 stages, as I told you a moment ago, we pass the unit onto the GPU, define some optimizer parameters from the model, and loss function. In this case, the loss function of the dice, just to be classic, let's say. And then we, in order to make the model as simple as possible, we divide it into slices. Yes, so I just get a slice by slice. I have defined here a two-dimensional unit, so it can only work on slices, just to preserve the memory. And when we are choosing the slices, I'm choosing only the slices that are where is it? Not here. I'm only choosing the slices that has anything positive, like here. Yes. So if the slice only has some spleen in it, it will be chosen. If that it does not have any spleen inside, it will not be chosen. Yes. So one more time, I'm getting this 3-dimensional array. I'm choosing slices over it. I'm checking each slice where it has the spleen in it. Yes. And then those slices are mixed among all of the mixed between all of the sorry, I'm tired. Mixed between all of the images, yes, and on this data we will train. Yes. Here we are fusing the slices for all of the images, and we can divide it into batches. Yes. So in case of the batches, it would go better. Yes. So we can get a train loader and train loader and pass train loader to k-iterator. But I do not want to keep it simple. Yes, so it will not be done like this in this particular example. So here in the epoch, yes. So when we are training the neural network, we are training this in the number of epochs. Yes, I had chosen 650 epochs, so it will take a couple hours to train it. And during the training, we have these these layers, which I shuffle the layer. It can be also achieved more cleanly, let's say, in the train loader, but getting the shuffle, changing the shuffle to the truth. Then I'm loading the data onto the GPU using the function from the CUDA.jl, so the q-iterator. It works extremely well in passing the data onto the GPU. Then this is a classic GPU training cycle for the flags. Then we are passing the checking the gradients and optimizing using those gradients. So we need one more time. Yes, we have the neural network. Neural network has some parameters. In order for the neural networks to learn the data, we need to pass this data, get the gradients in respect to loss functions. Then, using those gradients, we can optimize the parameters. And when we will get the best parameters, we will have the best, hopefully have the best performance. And then we are saving the model using BSON to some path in order not to lose the idea. So let's say we are finished this, we've saved it, and then we can load it and execute it. Yes, so the result of this is displayed already here because I saved it into the HDF5. So we loaded image, loaded label, divided into slices, executed for each by the in case each part by the model, passed the data onto CPU, checked the output, created the group to save it. Yes, and it was ready to visualize as you see now. Okay, do you have any questions for the moment? Basically, I finished, but I will also tell a bit more about what can be done further, what are the further directions, basically. But do you have any questions for now? Okay, I assume that there are no questions. Okay. So what should be done also in this neural network that I did not done for the simplicity's sake? In order for get a far better performance, we should augment data. Yes. So how does the augmentation of the data works? Data augmentation. Okay, here like this. Data augmentation is that we get some data and we modify this artificially in some way. Yes. So it can be, for example, a fine deformation, so it would change the shape. We can change intensity inside. We can rotate it. We can slice out some of the parts. Yes. There are a lot of possible. There's a lot of possibilities. Oh, thank you very much. There are a lot of possibilities that we can augment the data. Yes, so we can augment the data by modifying it to get the possible variability that we expect. Yes, so for example, in case of the lungs, yes, rotation, when we just zoom into the very particular spot, the rotations usually are very good. But if we are not zooming in and we are just looking at the whole lungs, for example, rotation would lose some information. This is quite a deep topic that needs an understanding. However, there are a lot of different augmentations depending on the case that we are and depending on the invariances that we want to achieve. So the invariance is one of the most important things basically in all of the deep learning. And what is invariance? In this case, invariance is lack of sensitivity to something. So for example, if we have a person, yes, the algorithm that is recognizing the liver should be invariant to some extent to the scale. Yes, so it should recognize that the liver is liver in a big and a small person. It should be invariant to translation. Yes, so whether we are moving it to some site. Basically, convolutional neural networks are invariant to translations. It should be invariant to some rotation, usually. It's not always the case, but usually. And some intensity modification, because, depending on the imaging, yes, intensity would be in the in case of the MRI, density in case of the CT scan. So this would be yes, all of this can change. And we know that it can change because this is logical. Yes, the liver can move. The person is breathing. The person can be bigger, smaller. The person can be obese. And when the person is obese, will have a lot of fat, and the intensity and the radiolucency will change. Okay, so what kind of augmentation is used for CT images? Yes, it's one more time depends on the particular case, but usually the most important are these spatial transformations. Yes, so like translation, like in some cases rotation. Although in many cases I do not use rotation because rotation can lose some information. Basically, if you imagine, yes, that something can be done, that something can change, and you can synthesize the data that will look like this changed data, it's good to do. Yes, for example, in case of the liver, we know that we are breathing. So translation up and down is common. Yes, it's normal. So when we would augment the data by translation up and down, we would learn the neural networks for the cases that are normal. Liver does not rotate 90 degrees. Yes, so it's not normal. So if you would add the augmentation that rotate the liver 90 degrees, it will the neural network will learn something that is fiction. So it's not useful, basically. At least in principle. But if we would look, for example, at the I don't know, at the nodule in the lung, yes, it can look basically the same whether we rotate this and or not. In some cases, switching the intensity is important. In some cases, intensity, like, I don't know, for example, in the suprarenal glands, intensity is quite stable and is typical for the disease. Yeah? So shifting the intensity will lose the information. So what augmentations exactly are good for each case is depending on the problem. Yes, some augmentations like translations are usually the good case. Usually the intensity transformations are the good case, but there is no one solution for all. Basically, it's problem dependent to a big extent. We want to synthesize the data that is probable to happen in real life. Okay, this is the idea. So this is the first thing that should be done. Yes, these augmentations. The data should be analyzed in 3D, not in 2D, as I did. I would choose some different metric, or at least choose different metrics and try different metrics out in the hyperparameter tuning. The hyperparameter tuning here should be performed by trying different architectures and so on. So basically there are hundreds of possibilities that we can do here. What is also important, and this is one of the reasons that I want to work with Julia, is that we can do all of it, all of those processes, so augmentations, different metrics, different steps, we can make it differentiable. And if we can make it differentiable, we, at least in principle, can do it as a one big optimization problem, not as a hyperparameter tuning problem that is harder, but far more efficient optimization problem. I am, for example, now working on the prostate MRIs, and I am working to fuse different architectures. Yes, so fuse, for example, the supervoxel architecture with the neural network, the Siamese neural network, with the graph neural network, and all of them put into one big chain of the back propagation. This is just the work that I started, so I cannot show you any results. But this is something that would be extremely hard to achieve in another language. Okay, so basically this is all that I wanted to cover for this. We have still 15 minutes left, so and I just wanted to add one more thing. Yes, so I will post also here my email. Or maybe not. Maybe better. Okay. Yes. If you would want to work on something like with this, you can just mail me. We can. I have some access to some data. I have a lot of work to do. And if you would be interested in writing some publication, getting deeper into the topic, we can devise some idea and we would work on this together if you want. Also, if you want to get something about the tools, I am also I would try to be as available as possible. You can catch me on the mail, you can catch me on the LinkedIn, or just write the post on the some of my repositories. Basically, repositories are work in practice. I would like also to parse the ITK to the pure Julia. Yes, so get because ITK is written in the C++. Yes, so and simple ITK that we are using here to load the data could be in principle get just from the C++ into the binary builder, and those problems that happened today should be avoided if all of this would be passed in the pure Julia, passing it from the C++ for the data loading. Also, there I should mention that in the link, there is also the set of repositories that I'm not an author of, but they are also very useful by the person called Dave Black. There are some medical augmentations, yes, some distance transformations, calcium scoring. Basically, I used these for units and for a lot of other things. They are very useful to look if you are interested in this topic, and they play well with my tools also. So you can choose whatever you want and compose whatever you like. This is the strength of the Julia, and I wanted to keep it like that. So thank you very much for listening to me, and I'll be still here and waiting for any questions and any discussion if anybody wants to discuss something. So thank you very much, and see you. Thank you for listening. Thank you for participation. Okay, I hope that it will be useful for you. Thank you. Okay, I don't see. Yes, you can use it with the Dicom images without any problem. Basically, ITK. This is using the ITK, yes, and simple ITK or Monai, and of course the basically the most prevalent way how to handle the data in the clinical setting is the Dicom, and they support Dicom as a whole. Also, what is important, there is a dicom.jl, yes, so we can also load it, the data into the arrays using dicom.jl. And I did not shown here, but the documentation is also quite nice. So yes, thank you for the question.